Good afternoon, everyone. Welcome back to another exciting video in Blackboard Engineering. Today, we're going to be covering a very important concept inside our MIP 32-bit processor, the ALU Control Unit. This is the part that allows us to control the different parts of our CPU, specifically how the ALU or the arithmetic logic unit operates. So it's important to realize that today we're going to talk about three things. We're going to talk about the theory behind the LEU control logic. We're going to design the control using the gate first, and then we're going to go ahead and implement a way easier and a scalable way of our logic unit. And that's when we're going to use the microprogramming to and use a ROM. So let's go ahead and dive into the theory of the LAU control. So the LAU control is this one. This is the LAU control unit. It acts as the middleman for our LAU. This is the LAU, and this has an operation signal, and it's gonna be 4 bits, and this is gonna send the control signals to the LAU. Remember, this one has X and this one's Y. This is going to be 32 bits. And this is going to have an output that also is going to be 32 bits. And this is going to be our arithmetic logic unit. This has an OPR here, precision control. And this is our main control unit, which has a signal going to our LAU, which we're going to call ALUOp, and that's going to be 2 bits. And then from our instruction memory, we're going to have a function signal, and that's going to be say bits. And also from our instruction memory, we're going to have an operation. And that one is going to be 5 bits. So depending our operation is how our LEU behaves. We have a multiple type of words that I'm going to present now. So how this gets this gets their control information. Well, in MIPS we have 3 types of words or instructions. We have the R types, and this is going to be the format. This is going to be from 31 to 26 bits. We're going to have from 25 to 21. We're going to have from 20 to 16. We're going to have from 15 to 11, 10 to 6, and 5 to 0. And the way this was divided, this is always going to be a 0. This is the RS instructions. This is the RT instructions. This is the RD instructions. This is the shift amount instructions. And this is going to be my functions. And then we also have branch instructions. And that one is kind of shorter, but it also has 32 bits. So from 31 to 26, from 25 to 21, from 20 to 16, from 15 to 0, and this is always going to be a 4. This is going to be an RS, this is going to be an RT, and this is going to be an address. And then for the last instruction, we have a load word or store word instruction, and it's going to be similar to our branch instruction. So this one also has 4 sections. But if my instruction is 35 or 43, then it's classified as a WR or SW function. This is going to be our RS, this is going to be our RT, and this is going to be our address instruction. And the way it's divided is the same as the branch. 31 to 26, then 25 to 21, 20 to 16, and then lastly 15 to 0. And this is our 3 types of instructions that we have on our CPU. Okay. So once we talk about this, we have to talk about the requirements of our CPU. So we can start with our opcodes. So for low word, we have that's gonna be represented as a 00. And then we're gonna have an operation because that's what we want. And this is gonna be a low word operation. And we don't care about the function field. We just don't. And now we want to talk about what do we want the LAU to do. Well, in the low word, we want our, I put here a word. We want our LAU to add. And to add, remember when we were building the LAU, it's 0010. Remember the mocks that we built on the LAU? And we have an AND gate, we have an OR gate, we have add, and then we have a way to convert the add to a subtraction. We use, I think we use a multiplexer to invert the bits into the 2 complement. And then we finally have this select them. So we also want to store word, and to do that, we use the same bits, 0 word. We also don't care about the function field, and we're adding again. So to add, we use the same bits on the ALU control. Then once we define that, we want to define our branch instructions. And to do that, we use a 01, and this is a branch is if is equal. We also again, don't care about the function field. But this time we wanna subtract. And to do that, the ALU must have this instruction, because this one will invert the second bits. And now we can go ahead and define our R types instructions. And to do that, it's always going to be 1, 0. We want to add, and our function field will be defined as 1, 0, 0, 0, 0, 0. And that's going to be an add. And you guessed it. Yes, it's 0, 0, 1, 0. Then the other instructions subtract. And that's going to be a 0, 1, 0. And that's going to be a subtraction. And to do that, this is 0, 1, 0. And then I want to end. And that's going to be 100 to 100. And then we want the LU to end. So that's 0, 0, 0, 0. As you can see, it's right here. So that's 0. And then we want to OR. And that's going to be 100 and 101. And that's going to be an OR gate. And that's going to be 0, 0, 1. Now, finally, we want to select if it's less than. And to do that, our function field is going to be 10, 10, 10. And that's going to be 0, 1, 1. So if we try to implement this, it's going to be extremely hard. So what we can do is start minimizing the equations. So minimize. So the way we're going to minimize these equations is by watching our original requirements and trying to minimize what we can. For example, if you see the first two, you see this one and you see this one, they both have the same operation. We also don't care about the function field. And if you see the ALU control, then they're both the same. Therefore, we can condense these two. We can say that for our ALU operation, if it's 0, 0, don't care about the function field. And you use this operation. 0, 0, 1, 0, because that's addition. And then for the next instruction, we have 0, 1. Well, we have a 0, we have a 0, we have a 0. However, if we get a 1 here, then obviously that's a branch equal. So what we can do instead is we can make this one a don't care. We don't care about this one. We only care about the 1. So because that's true, we can define our next instruction, and that's x and 1. And the same, we don't care about the function field. And to do that, we are going to do a subtraction with 0, 1, 1, 0. and that's a subtraction. Now, this is where things gets interesting for the next instructions. Well, if we get a 1 here, we know we're talking about the R type. And if you can see, no other have a 1. So because we have a 1 here, then it's obvious that we have an R type. So we can translate that into 1x. Because if we get a 1 on this bit, then it's obvious that it's an R type. And we don't have to worry about the 1-1 condition because we don't have a 1-1 condition. It's never going to happen because remember, this depends completely on the word instructions. So you either have a 0, you either have a 4, or you got a 35 or 43. So we're never going to have a 1-1. So because we have that, that tremendously minimizes our operation. So we have 1x for the first instruction. We can say all of this, we don't need it because they're all the same. So we can define that as don't cares. And we can make them x's. And then we only care about this side. Therefore, we can say don't care, 0, 0, 0, 0. And that's going to be a 0, 0, 1, 0 or an addition. Then our next instruction, 0, 0, 1, 0. Same, don't care. And our next instruction, it was a subtraction. So it's going to be 0, 1, 1, 0. 0, 1, 1, 0. And that's going to be a subtraction. Next, for our next instruction, it's going to be don't care, 0, 1, 0, 0. All 0 because that's the instruction for the ALU operation. And that's going to be an AND. And then for our next instruction, x and x, 0, 0, 0, 1. 0, 1, 0, 1. And it's going to be 0, 0, 0, 1. And that's going to be an OR operation. And then our final operation is going to be our 1x, x, x, 10, 10. And that's going to be 0, 1, 1, 1. And that's our LST operation. And this is our table, our minimized table. Now that we have derived this minimized table, we're able to derive our outputs. So if we, for some reason, let's say this is F5, F4, F3, F2, F1, F0. We got 6 outputs here. We got ALUOp 1, ALUOp 0, and then we have OP 0, OP 1, OP 2, OP 3. So let us start with OP 0. So the way we're gonna derive this is we're gonna see where's up 0, 1. Well, the only place that up 0 is 1 is for this one and this one. So this allows us to see um, what conditions are these two making these ones. So let's take those two in consider for O 0 is equal to 1. We had that 1x, x, 0, 1, and that one is, I got a 1. I got another one here, xx, 1, 0, 10. And remember, this is an OR, this is SLT. So if we see here, the only moment this is a 1 for this one, for this condition, is when this one is a 1. And you can see that no other is 1. So we can say that for the first one, we actually have 1x, and we only care about that one. And then for the other one, we can say the same thing, because if you see, those are zeros. So if we want to derive those equations, then we have that for the first one, we have ALU of 1 ended to F0. And for the bottom one is ALU of 1 at 5. Oh, I'm sorry. It's this one. F3. And if we derive those two equations, or ALU, then we can apply the distributive rule, and we can extract these two out like common factor, and we have ALU of 1, F0, or F3. And this is our equation for OP0. And we can do the same thing for the other ones. For OP1 when it's 0, this one is a little bit tricky because for OP1 we have multiple ones. So we have to see them all separately. So for this condition, 0, 0, we need that one. We don't care about the function, but we do care about that one. So 0, 0, function field don't care. And okay, so I have a 1 for that one. The next condition is x1, and that's another condition. And then we have three conditions for those ones. And that one 0 1 0. And the final condition for 1. So we have to see a pattern in all of them. What's the pattern? So let's see. These two, we have both don't cares. So we have to see if there's a way to combine them. So when we see 0 and x1, the output is the same for both. So that means the only difference is this 0 and 1. Could it be that it doesn't matter? We don't care if it's 0 or 1 as long as this is 0. If that's true, then that means that we can specify this first one has to be 0. The next one, we don't care. Same, we don't care about the function field. And that's a 1. Now for the second one, for this ones, we have to see if there's a way that we can combine all of this together. So because this is a 0, we only care if it's a 0. That means anything else we can wrap around that to the other following instructions. So we don't care about it. Because if it's a 1, it's automatically that one. But if it's a 0, then we're gonna force the first instruction. And then we gotta see what's common about these ones. So obviously it can be this one because this one changes and the change. So it's either this one or this one. So the way we're gonna decide which of those two correspond to these ones is by a quick inspection of this table. So we need 3 ones. So we need this one, and this one. And that one correspond to, so it's not this one because that one has a 0. I don't care about that one. So there's a 0 here, a 0 here, 0. That's something in common. So it matches. The other option was the last one. We can say that that one is an option, that one's an option, but we have a 0 here. So that completely disregard that one. So that means that for the second one, we can say we only care about the second bit. So 0, 1, 2. So don't care about those one. Don't care. I care if it's a 0, then don't care, and that's a 1. So it seems we were able to simplify our huge equation into ALU up 1 inverted or F2 inverted. Thus, OP1 is equal to ALU inverted or F2. And now for second operation, we have OP2. We have to go back to the equation and see. So we don't care about that one, it's a 0, but we do have the second one. So X1, the other ones are don't care. I have a 1. The other one is this one. That one is an R-type equation. So we have 0, 0, 1, 0. Then the last one is 10, 10. So we do need this condition. So that's a bunch of don't cares. Now we have to see if there's a way to combine these two. And it clear there is. So if I have a 1 here, I don't care about that one. And I see a 1 here. So as long as that one, this is a 1, then I should have a 1. And that is for the first one, ALU up 0 or ALU up 1 ended with F1. And that should give me a 1. Thus, OP2 is equal to or and that's our second equation. And then finally, for our P3 is equal to 0, because if you see, that's always 0. So that's simply 0. We just have to find, we can ground it, or we have to find a condition that guarantees that OP3 will always be 0. And that's it. So our circuit implementation, instead of being one complex one, because we optimize the equations really well, it's gonna look very simple. So for the first one, we can define OP3. So we can say that this is an inverter, and that's OP3, and that's gonna come from our ALU OP1, because it doesn't matter. If it's 0, then it's 1, and then this is an AND gate, so the output is always 0. for our OP2, we're gonna have an OR gate. One side is gonna be ALUOp 0, and then the other one is gonna be an AND gate OP1, and then we're gonna have the F1 input going into that one, and that's for OP2. And then for OP1, we're gonna have this right here, OP1. We're gonna have an OR gate. We're gonna have an inverter here, and then we're gonna have OP1 going to the inverter. We're gonna have F2. I'm gonna put it right here, and that's gonna be our OP1. And then for our OP0, we're gonna have an AND gate, and that AND gate is gonna have two inputs. One is gonna be an OR gate, and the other one is gonna be LAOP1. So and then to our OR gate, we're gonna have F0, and we're also gonna have F3. And obviously we have F4 and F5, but they don't cares. And this is our circuit for our arithmetic logic unit controller. Arithmetic logic unit, well, control. So this comes from the instruction memory. This also comes from the instruction memory. And these ones go to the ALU. And this is how you implement the control unit. From our very complex equations that we usually have, we manage to minimize it, simplify it, and allow us to build with a few components. Now, we're gonna try to implement this in Logisim, but then after that, we're gonna do it in ROM because it's easier. So now that we have designed our game implementation, we're ready to do the project on Logisim. So the way we're gonna do it is we're gonna use the same gates that we had. So for example, we had an AND gate here. One of the bits where was embedded. And remember, this was our OP3. Was AND here. And that was our ALUOp 1. Then we have a OR gate here. That one was our OP2, and that one came directly from OP0. Then we have an AND gate. One of the outputs was from OP1, and the other one was from F1. And then we have an OR gate, both of their inputs negated. Down was our OP1. Here. And then we have our off, our F2. And then finally we had an OR gate here for our final gate. That was our OP0. For the caps. We had an OR gate here. Our F0. And we have our F3 here. Oh, it took it. I don't know what happened. And then this one came from ALU PC1. And then we have our F4 and F5, which we don't use because they're don't cares, but we're gonna leave them here. So we have the connections available. And that's it. So if we remember from our table, let's see, where's that table at? We have that for 0, 0. We have 0, 0, 1, 0, and that's an add. We have an add here for 0, 0. And it really doesn't matter these options it will always show 0010. You see, 0010 because that's what we want. We want an addition. Now, if we will put 01, then we have a subtraction. Now, if we do a 1, then we are in the archetype instructions, and then it depends what I have there. So for 10, I have 0010. That's subtraction. 10, 10. So 10, 10. I have a LT instruction, and this is our circuit for our control unit. However, we want to build this as a ROM because it will facilitate us, and it looks nice too. So all we got to do is define that we have 8 addresses because this is inputs. So 1, 2, 3, 4, 5, 6, 7, 8. 8 addresses, which we do. And the output is going to be 4. So 4 outputs. And the way we're going to do this is we have a little script that we can use. Which I already have over here. I'm just going to copy paste here. And this ROM will help us build the program that we need. It's very simple. The conditions is here. This is the same condition that we use. For example, if we have 1, 1, that condition is not used, so I want to output a 0. If OP0 is 1, then I want a 6 because this is the same as 0110. If I have a 00, then that's either a load word or stored word instruction, so I want an addition. And then we have the archetype instructions. So if function is all 0, then I want an addition. If I want a 2, then I have a subtraction. If I have a 4, I have an AND. And then they output that information here. And then it will output that into the file. So now that we have coded that, either we might have to fix something here. Let's see. ALU control. We can run it. ALU control file. And we gotta find that file where it's at. Well, the file is saved since I didn't specify where I want it. It's going to be saved on the working directory of the Visual Studio Code. For this computer, it's inside my application data file folder. And if I find it here, then I can open that file. And this is our program for our ROM. If you can see the first 63 selections, this is for 00. It's not always going to be an addition. And then the following is going to be a subtraction. And then for my archetype, it's going to be this program. And the other ones doesn't matter. We don't care about those. So now that we have this file, we can go ahead and save it on our desktop. We're going to click save. Then we're going to go back to our ROM. We're going to click it. Content. We're going to tell it to open it. We're going to go to our desktop. And this is our program. And if you can see, it has the program loaded to it. We can select our input. That's going to be 8. And then we're going to have our output. That's going to be 4. Now, if you can see, as long as OP0 and OP1 is 0, my output is going to be 2. I don't care about my functions. If I go to 0, 1, then I have a subtraction. Same. It shouldn't matter because they all don't cares. So it should output the same instruction. Now, if I go to 1, 0, I have an addition for my first archetype. And then I have for 0, 0, 1, I have an AND, just like we have here. Well, and 0, 1, 0. So 0, 0, 1, 0. There you go. That's 0, 0, 0, 10. Yeah, that's a subtraction for the instruction 10. So this is how you implement the ROM at the ALU control unit using a ROM. I like this approach, and this is the approach I'm going to use. I'm going to use ROMs to be able to program our ROM because that will help us expand in the future without having to this will help us expand in the future without having to reprogram, to implement the whole gate. I just do a program and it will do the next uh, additional selection that we have to. All right, everybody. So that wraps up our deep dive into ALU Control Unit. If you think about it, we started this video with the theory behind how MIPS instruction type guide ALU operation. Then we moved to our gate level implementation, and I shall also show you how to program the microchips using the ROM for full control signal decoding. If you follow along, well, let me tell you congratulations, you just built a crucial part of a working MIPS CPU. And if you're building this step by with me, you're well on your way to be building your own processor from scratch. If you found this video helpful, give us a thumbs up so YouTube know this content is worth sharing. And if you're new here, consider subscribing. This is the only one piece of full CPU design series, and there's so much more coming. As always, thank you for spending your time here at Blackbody Engineering. I'll see you in the next video that we're going to be covering the control unit, one that is the most important part of our CPU. That's where we keep engineering from the ground up. Stay curious and keep building. Thank you.